Good morning to one and all. I am Dr. Tirupataiah Kasani, Assistant Professor from the Department of Mechanical Engineering in School of Engineering and Technology, Adamas University, Kolkata, India. I welcome you all for the next class in the module Unconventional Machining Process, Class 3. That is, we are dealing or we are starting a new unconventional process with the contents, introduction, working principle, material removal mechanism, applications, advantages and disadvantages. And the name of the next unconventional machining process is electrochemical machining process. Till now, we have seen in the module 1 abrasive jet machining followed by ultrasonic machining. In the Section 2 or the class 2, we have already seen the electric discharge machining EDM process, and now in the class 3 of the module unconventional machining process, we are going to deal with this ECM electrochemical machining process. Okay, see here, this is the electrochemical machining process. Okay, see here, yeah, this is the electrochemical machining process. Schematic of ECM setup is as shown here. This is the electrolyte and filtration, electrolyte reservoir, and this is the pump. These are different parts. This is how the ECM setup. See here, as the name itself is indicating electrochemical machining. The machining process is happening with the help of electrical and chemical. Means electrochemical machining process. Earlier in the electro discharge machining, the electrical energy followed by the thermal energy is used for the removal of the material from the workpiece. Here, the chemical energy is used for removing the material. See here, this is the electrolyte. What is an electrolyte? An electrolyte is a medium, okay, which will be used for removing the material from the workpiece. Okay, that is the electrolyte, and this is the filtration. The filtration purpose, as we have already seen, the removal of the chips in the electrolyte medium here. Earlier, the dielectric medium in case of EDM. Okay, see here, this is the electrolyte reservoir. Electrolyte reservoir is the one which is supplying the electrolyte medium to the machining zone. Here, after the use of some time, the electrolyte concentration may decrease. That is the reason why continuously, time and again, this electrolytic reservoir is filled with a fresh electrolyte medium. Okay, whenever it requires. If the machining efficiency or the machining removal rate, material removal rate is decreasing, then we are going to replace this electrolyte medium with a fresh medium. Generally, the electrolyte medium used in most of the cases is NaCl. Okay, see here, with the help of this pump from the reservoir, we are sending this to the filter. See here, here it is the filtration process. Means this is the electrolyte which is collected from the machining zone. Here, some amount of the chips will be filtered out using this. Okay, some contaminations will be removed from here. If any will be present, will be recirculated or filtered here in this filter. Okay, the electrolyte is supplied from this pump to the filter and it is sent to the tool. Here, see here, the tool is hollow in shape. This is the electrolyte medium and this is the tool. You already know that the workpiece is the positive and this is the negative. Okay, workpiece will be mounted over the table which will be moved in x and y directions, and this workpiece will be fixed with the help of the fixture. Okay, this is the base or the table, this is the fixture and this is the workpiece. As you already know that the shape of the tool and the cavity that is produced over the workpiece are same. Okay, see here, the flow of the electrolyte, if you observe these arrow marks, the flow will be from here pump to the filter to the tool to from here this to the this electrolyte medium. This is the flow. Let me enable this pointer. Yeah, electrolyte medium is electrolytic reservoir to the pump to the filter to the tool and to the machining zone, from here to the electrolyte collecting tank. From this filtration Again, the fresh reservoir pumping. This is a closed circuit, means closely the electrolyte circuit is closed. It is continuously circulating. Now we will see this is the power supply to the tool, means this is the voltmeter and this is the ammeter, means the negative and the positive terminals will be given to the tool and the workpiece respectively. Okay, this is the workpiece. This hatched region is the workpiece. See here, this is the fume extractor. Okay, see, whenever there is a power supply will be given to this, whenever there is a power supply will be given to this, and the electrolyte is supplied to it. Okay, for example, the anions and cations. What is this? What is the basic principle? This is the Faraday's law of electrolysis. Means dissolving the ions. Means in the electrolyte, positive and negative ions are the responsible for the removal of the material from the workpiece. Whenever there is a power supply will be given to the electrolyte medium, and this circuit will be closed. Means here the chemical action will be occurred between the workpiece and the tool in the electrolyte medium. Here the ions, means whatever the workpiece material that is dissolved in the electrolyte. Okay, this is the whatever the material that is removed from the workpiece in presence of this electrolyte is trying to accumulate over the top surface of the tool, but there is a flow, continuous flow of the electrolyte medium. That is the reason why before it is accumulated, before the workpiece material is accumulated over the tool surface, that will be taken away from the machining zone by the flowing electrolyte, and that will be collected in this electrolyte. Okay, the chips are extracted and again the same will be circulated. Okay, this is the reason why, of course, the tool movement is by the servo controller. The feed motion is very precise. Okay, here what are the process parameters? Here the feed motion and the concentration of the electrolyte and type of the workpiece that you are using and amount of energy, that is power supply, that is given to the tool and the workpiece. Okay, all these are means for the electrolytic action, are you adding any additives to it as a catalyst to increase the rate of reaction? All these are the process parameters which can control the material removal in this region. See here, if any chemicals will be evolved from the workpiece material during the machining process, all those will be extracted out through this fume extractor. Okay, this is the machining zone. Okay, is it right? See here, a schematic of material removal in ECM, electrochemical machining. Electrode feed, that is the tool. This is the tool, that is cathode negative, and anode is the workpiece. See here, 10 volts will be the, and this is the flow of the electrolyte. This is the shape of the tool initially over the bottom surface of the tool. Okay, and the same shape will be replicated over the workpiece like this. The same shape will be replicated over the top surface of the workpiece. However, the material removal in this portion is due to the presence of this electrolytic flow, electrolytic medium. Okay, positive ions, negative ions. So by that time, the workpiece material is trying to accumulate or deposit over the tool surface. The electrolytic medium will take away that material. Okay, that is the principle. See here, the same shape is replicated over the top surface of the workpiece, that is anode. The feed motion is continuous. See here, steady state gap means a minimum gap of 0.4 mm is maintained. Why? Because there should be a flow of electrolyte continuously between them, between the tool and the workpiece. Otherwise, the chemical reaction won't happen in the electrolyte and the material doesn't remove. Okay, that is the reason why a constant gap is maintained and the continuous flow is also maintained. That these are the two necessary conditions. See here, ECM electrochemical machining is characterized as reverse electroplating, means it removes metal instead of adding it. Okay, all of you know the electroplating means depositing the one electrode material over the another. See here, this is the reverse electroplating, means may actually the whatever the material that is removed out from the workpiece is supposed to be deposited over the electrode. Okay, that is the electro that is the reverse electroplating, but this is not happening. Why? Because due to the continuous flow of the electrolyte medium, whatever the removed material from the workpiece will be taken away from the machining zone. Okay, ECM depends on Faraday's law of the electrolysis process, and electrolytes play an essential role in removing material. See here, what are different types of electrolytes that we are using? NaCl is one kind. Okay, some applications, if the metals will be machined using ECM, sulfuric acid, the king of the chemicals, that is H2SO4, is also used as electrolyte. Means depending upon the application, depending upon the material, a suitable electrolyte medium is selected for the process, that is ECM process. Normally used for mass production and for hard materials that are difficult to machine using conventional process. Okay, which are difficult to machine using conventional process, this is a unconventional process or non-traditional machining process. Okay, this is the ECM process used for those kind of materials which are hard to cut using conventional methods. Both electrical energy and chemical energy to remove the material, as we already see, whenever there is a power supply is there in the electrolytic medium, the reactions will start positive and negative ions. Those are responsible for the removal of the material. Okay, that is well known. Here, see here, Faraday's law of electrolysis. The weight of the substance produced during the electrolysis process is directly proportional to the current that passes through, the time duration of the process, and the equivalent weight of the material. Means Faraday's laws of electrolysis, the weight of the substance produced during the electrolysis process, means the amount of the material removed from the workpiece is directly proportional to the current passed through it. If more amount of current will be supplied, then more amount of electrolytic reaction and more amount of material will be removed. The time of duration, if more amount of time the chemical is exposed to the workpiece, then more amount of material will be removed and the equivalent weight of the material. And this is the chemical terminology that you people are well aware. And they say, what are the essential? Both the tool and the workpiece are conductive and ionic in nature. Earlier, in case of EDM, conductivity is fine, but here ionic and conductive and ionic, both. Okay, in case of EDM, conductive is fine, but here conductive plus ionic. The tool and workpiece are immersed in an electrolyte. There in dielectric, an electrically conductive fluid that this is. There in EDM, there is no such electrical conductivity through it, that is dielectric medium. See here, the anode and cathode, positive and negative. The anode loses material to the cathode, that is supposed to be happen, but generally due to the flow of the continuous electrolyte medium, that will be taken away from the machining zone. Generally sodium chloride, okay, NaCl, sodium nitride, potassium chloride, KCl, sulfuric acid, H2SO4 are used as electrolytes, okay, depending upon type of the material that you want to machine using this ECM process. Mechanism of material removal is ionic dissolution, that is happened in the electrolyte medium that is flowing between the tool and the workpiece, right? Yeah, that is the ionic dissolution, positive and negative. The typical material removal rate will be the 0.097 to 0.0371 mm cube per minute. And this typical MRR data is taken from the research papers. Okay, this is just for your understanding purpose, just for your reference purpose. These are not standards, okay, but these are the typical material removal rates taken from the literature that is available. Electrochemical machining process. The main functions of an electrolyte in ECM. Okay, what are the functions of this electrolytic medium? Okay, electrolyte medium in ECM. It carries the current between the tool and the workpiece. That is obvious. Okay, it removes the products of the machining and other insoluble products from the cutting region. See here, machining products, that are the chips or any other compounds that are formed in the machining zone due to the machining process, and other insoluble products from the cutting region. Okay, all those will be taken away from the machining zone. It dissipates heat produced in the operation. Okay, as you have already seen, this is the NaCl. Okay, the amount of, if at all some amount of heat energy is produced due to the chemical action of the electrolyte medium, if the tool and the workpiece are subjected to some amount of heat, this electrolyte itself is taking away that amount of heat, that excess amount of heat, and the temperature of those two will be maintained at certain levels so that their life won't be decreased drastically. Okay, if why? Because every time a fresh electrolyte medium is exposed to the workpiece and the tool, okay, if it is standstill at that position, then the reaction may be high. Okay, that is the reason why, if at all any amount of heat is accumulated during this reaction, either at the tool portion or at the workpiece portion, that excess amount of heat will be taken away by the electrolyte. And the essential characteristics of electrolyte include, what are the characteristics? These are the functions. Okay, now when it comes to the characteristics, good electrical conductivity. Okay, non-corrosive property. If the electrolyte is having a corrosive property, all the machine equipments will damage. That is the reason why non-corrosive property is important for the electrolyte medium. And non-toxic and chemical stability. Okay, chemical stability means during the machining there should not be any byproduct, any further byproducts formation. That is the chemical stability. There is no further reaction of that chemical, whatever you are using as electrolyte medium during the machining or after the machining process. That is non-toxic. Why? Because if it is a toxic, that will be harmful to the humans if it will be inhaled. And low viscosity and high specific heat. All of you know, this is the low viscosity for increasing the flow ability of the electrolyte through the intricate portions, that is through the thin regions or the small portions of the workpiece or the intricate shapes. Okay, to flow it, the low viscosity is the one of the characteristic for the electrolyte medium. Okay, next, the high specific heat. If the specific heat is high, then if at all some amount of heat will be raised at some portions of the workpiece, then that will be easily taken away if it is a high specific heat electrolyte. And now the process parameters include the voltage, inlet and outlet pressure of the electrolyte. See here, the inlet and outlet pressure of the electrolyte, these two will be maintained constantly. For example, if these two will vary, then there may be excess amount of material removal or less amount of material removal. Okay, that is the reason why it is better to maintain both at same level, at same level. And the next one is temperature of the electrolyte. Time and again, we are going to check the temperature. Either this is due to the machining or due to the exothermic nature of the chemical. Okay, that is electrolyte, exothermic reactions of the electrolyte. That is the reason why we are continuously going to check the temperature of the electrolyte. If it is very high temperature, then we are going to cool it down for some time. Or we can replace that with a fresh electrolyte medium. And the next one is the tool feed, that will be with the help of the servo motor. Okay, for precisions, for high precision. And now we will see the ECM applications. See here, this is the die sinking. ECM applications are the die sinking ECM. Why? Because the tool and the workpiece both will be immersed in the same as in case of EDM, that is in dielectric medium. In case of ECM, that is electrolyte medium. And profiling and contouring and trepanning this trepanning is one kind of tool. Okay, one kind of the machining operations to create the hollow regions. And this is the grinding process and drilling process and micro machining and pulse ECM. Most common products are turbine compressors or blades and rifle barrels. See here, this is the die sinking. What this die sinking means? This is the workpiece and this is the tool. Means the shape here, the flow of the electrolyte is in this portion. Okay, see here, this is the 3D profiling of the turbine blade. See here, the flow of the electrolyte is like this. Okay, from here to here. Means precise control. See here, in case of drilling, here, see here, the flow of the electrolyte is from here to the here. This is the workpiece and this is the tool. See here. See here, this is the tool portion and this is the mask region. Why? Because the mask region will be provided in this portion for the tool to protect it, to protect the tool from the reaction of the electrolyte. Okay, here the reaction is required to remove the material. Here it is required, but here, if the reaction is happened with the electrolyte, okay, chemical reaction will be happened from both the ends, the material will be removed. But from the tool, the material removal is not required. But the material removed from the workpiece is required. That is the reason why to protect the tool in this portion, we are providing a resistive or the mask medium, which protects the tool from reacting with the electrolyte. See here, these are the two components. See here, ECM advantages and disadvantages. Well suited for the machining of complex two-dimensional shapes. Okay, this will be, if you see that ECM, the 3D profiling. Okay, that is the 2D, two-dimensional shapes. Delicate parts may be made. Little or no tool wear and difficult to machine geometries can be machined. Difficult to machine geometries can be machined. Large cavities are more economical on ECM and can be made in 1/10 time of the time in EDM. See here, the advantage of ECM. Large cavities are more economical on ECM and can be made 1/10 time, means time saving and economical, both. Okay, means depending upon the application, which type of unconventional machining process is to be selected. That is very much important. The disadvantage, when it comes to the disadvantages, the initial tooling is high, of course, and environmentally harmful byproducts. If the electrolyte is forming any kind of byproducts or the harmful gases during the machining process in its reaction, due to its chemical reaction, then that will be harmful to the people who are working surrounding it and the equipment and also to the environment. And complicated tool design is difficult. Why? Because the as I told, the protection of the tool material at narrow regions or at intricate shapes is very much important. Okay, if I will design a tool for ECM process with fine features, after making certain components, the tool itself will wear and I need to make a fresh tool. The tool making cost is very high. Okay, means even though means that is taking more amount of time for manufacturing or fabricating the ECM tool itself. That is the reason why complicated tool design is difficult. Okay, why? Because the flow of the electrolyte through it, that is one thing, and sustaining or using the same tool for manufacturing the number of components, that is the second thing. These are the two disadvantages. That is the reason why complicated tool design is difficult. High power consumption, because the amount of material is removed by the action of the chemical energy and electrical energy. Due to the supply of electrical energy to the electrolyte medium, the chemical reaction will happen and means the same chemical energy is used for removing the material, means the power consumption in this process is very high. See here, Till now, we have seen electrochemical machining, ECM. See here, electrochemical grinding, what it is. See here, what this is. Oh, sorry. Yeah, electrochemical grinding. See here, schematic diagram of electrochemical grinding setup. See here, this is the storage tank of electrolyte, and this is the pump, and this is the filter to extract the debris or the chip form during this machining process. And see here, from this, it is fed to the, this is the grinding spindle. What is this? This is the workpiece and this is the work table. This is the work table and this is the workpiece. Means the material removal is supposed to be happened for the workpiece using this electrolyte and the grinding wheel. See here, the electrolyte is fed from here to the here. Means on one end or one periphery of the one side of the grinding wheel. Okay, grinding spindle. This is flowing like this, like this, like this. Means there is a gap between the workpiece and the grinding wheel. See here, there is no contact. That is the reason why we are calling this as unconventional machining process. Of course, during the flow of this electrolyte medium, the chemical reaction will happen and the the material from the workpiece will be removed if it is a electrochemical machining. But here there is a term electrochemical grinding. That is the reason why I am not calling this as a tool. If it is an electrochemical machining, this is workpiece and this is tool. But this is electrochemical grinding, means this is workpiece and this is grinding wheel. But here the amount of material that is removed is not only due to the action of the electrolyte, okay, also due to the action of the mechanical grinding. See here, means for example, 90% of the material removal in the machining zone is due to the electrolyte medium, and 10% of the material removal in the machining zone is due to this grinding wheel action. Okay, grinding wheel action. That is the reason why 90% of the workpiece material is removed due to this electrolytic medium and only 10% by this grinding wheel action. Okay, that is the reason why electrochemical grinding. Electrochemical machining, we know using the grinding wheel we are taking or we are improving the material removal rate further. That is the reason why we are calling this as electrochemical grinding. See here, ECG, electrochemical grinding, also called as anodic machining or electrolytic grinding. Okay, electrochemical grinding is a process that removes electrically conductive material by grinding with a negatively charged abrasive grinding wheel. See here, electrochemical grinding is a process that removes electrically conductive material only, okay, by grinding with a negatively charged abrasive grinding wheel, the negatively charged abrasive grinding wheel, an electrolyte fluid, and a positively charged workpiece. We know that positive is workpiece. Materials removed from the workpiece stay in the electrolyte fluid. That is well known. That is in the form of chips. Working principle is electrochemical grinding combines both electrolytic action 90% and physical grinding 10% to provide precision, burr free and stress free. Okay, see here 90% will be the electrolytic action, 10% is by the physical grinding. Okay, people may ask that here 10% of contact between the workpiece and the tool, but here only 10%, but the material removal rate due to that direct contact, only 10% of the material is removing, but due to electrolytic chemical action, 90%. That is the reason why majorly we can call this as or consider this under the category of unconventional machining process. Okay, the electrolytic reaction ECG eliminates the need for a separate deburring operation. Deburring means the chips which are generated and which are having a slight contact with the machined surface. That is we can call it as burring, means deburring, removing those small or tiny chips from the machined surface. For that purpose, the electrolytic reaction ECG, this eliminates the need of this deburring action. Means if the 10% physical grinding is also present in ECG, then there is no chance for the formation of burrs. Okay, no separate deburring operation is not required after this ECG, because the ECG process doesn't require metal on metal abrasion. There is much less risk for thermal distortion, that is well known, and surface distressing, stress cracks, burrs, or scratches on the workpiece, capable of precisely grinding extremely thin and small diameter metal components. Okay. And finally, the low metal removal rate. Why there is a low metal removal rate? The rate at which the material is removed during the process is relatively slow in case of electrochemical grinding. Typically, it is around 15 mm cube per second, I think. Here, 15 mm. I think the units will be different. We need to cross check it once, which can impact the productivity for high volume production requirements. Okay, means low material removal rate will be assigned with this. Thank you. And in the next class, we'll meet or we'll discuss another unconventional machining process. Thank you all.